Welcome back. In the last lecture, we were talking about 1D photonic crystals, wherein we had a slab of multi-layer stack of different materials. So today, in this lecture, I want to introduce what is known as a diffraction grating. Okay, you can draw some parallels from what we have already studied. So in the previous case, we had this semi-infinite slabs in the XY direction, and we had incidence from the Z direction. Now instead, what I will do is I'll consider a periodic arrangement of different refractive indexes on a substrate. So if I have to expand this, this was a toy schematic. So if I have to draw a diffraction grating, it would look something like this. Let's say I'll have my structure substrate. On top of that, let me say I have some materials with different refractive indices. Okay, so it could be something like this, going in this infinitely in one direction. And so on. So effectively, this could be, let's say, just for example, this can be n equal to 1.5, and this could be gold. Okay, that's one possibility, gold, which is a metal, and then air. So this is known as a diffraction grating. The reason this is interesting is it exhibits some unique dispersion properties. For example, if I have a range of wavelengths incident on this diffraction grating, let's say from the top in this direction, there's a range of wavelengths incident. You will see that the way the waves bend is going to be dependent on the wavelength. Okay, so the reason it's called diffraction grating is because the origins of this, or the way to understand this is, it goes back to the phenomena of diffraction, which all of us have studied at some point. So the classic diffraction experiment was that, let's say you have two opaque objects, and then there's a small gap, there's a slit, single slit, and let's say the electromagnetic wave is incident on that single slit. It so happens that if you look at a screen which is far away, it forms what is known as a diffraction pattern. That is what is shown in the black and white image. That's how the light would look like. Of course, we are considering that it's a single wavelength. We'll address what happens if you change the wavelength. Okay, so how does this diffraction pattern look? So this is my diffraction pattern. Seen on a screen, right? So, you can actually see this in your own homes. Let's say you have a laser pointer, which is red color. You put a tiny, let's say hair follicle or something, and you shine it, or a metallic object which is very, very thin. You shine the metal on the laser on that, and then if you look at the screen far away, you'll see that there is a pattern of bright and dark intensities. But of course, I would advise you to be very careful. The lasers can actually damage eyes, so be careful that none of the light is going into your eye if you're trying this experiment at home. All right. So one of the unique features of this diffraction pattern is that if you look at the angular width of the central lobe, okay, so let me call this as delta theta. Okay, this is what I'm calling it as angular width. So basically it has a minima here and it has a minima here, and the whole thing is actually a sinc function. Okay, this comes from the classical diffraction theory. We don't need to get into all that, but effectively it's a sinc function. And it turns out that the width of the central lobe, delta theta, is going to be equal to 2 lambda by d. What this tells us is that, let's say if I have my wavelength to be 500 nanometers, and I have the slit width to be, let's say, 2 millimeters, then my delta theta is going to be very, very small. And in effect, you will get the same image on the screen. Okay, let's say my screen was large, right? So if I think of it, if I make my screen in this way, and this is my width of the screen, which is, in this case, I said d. If the d was very, very large compared to wavelength, d is much, much greater than lambda, then delta theta is small and image forms clearly. Okay, but the moment d is of the order or less than the size of lambda, what do you think will happen? Then delta theta is large. That means if you had an image like, incident, let's say the slit of this dimension here as I've shown, your image could be, I mean, you will not see a correct one single slit, but you end up seeing a broad intensity like this, and then there will be a slightly weaker intensity, weaker intensity, weaker intensity on both sides. Okay, so this is what is known as my diffraction pattern, and the extent to which the light diffracts or diverges after going through the slit is the extent of the strength of diffraction. Okay, so we can characterize. So this is known as a diffraction pattern, right? Diffraction pattern formed whenever your slit width is smaller than the wavelength or of the same order of the wavelength. Okay, and if you make it very, very tiny, then you get a lot of orders, but all of them might have very small intensities, so you'll have to actually take some precautions to observe that. All right, so this is diffraction pattern. So why does this help us? The reason it helps us is my array of these objects, like gold lines, let's say. So this, I can think of it as a two-dimensional crystal, photonic crystal, 2D, or rather, I will not even call it 2D. Well, it's not a photonic crystal in that sense, but it's just 1D variation in this in this direction here, and along this direction it's infinite. Okay, and in the Z direction just one layer. So I would not really call it a photonic crystal, 2D photonic crystal, but we will come to it. Okay, 2D photonic crystals in the next lecture. But for now, yeah, this is the diffraction grating consisting of parallel wires, let's say of gold. Okay, the reason this can be interesting is this. Now, as I said, the extent to which light bends is going to depend on the wavelength. To see how that happens, let's consider this scenario. Let me say I have a slit which is, okay, let me actually draw one straight line and then erase it. So I have, okay, no, I want a straight line. Okay, and then I'm erasing some sections of it. Let's say I have two slits of this form. I have two slits, equal width. Okay, and I'll also tell you that my periodicity is, in this case, this is going to be, my periodicity is, let's say, in this case, let me say this is A. Okay, what happens when light is incident on this? The way to analyze this is, let's say I have my light beam which is incident from the left at a certain angle theta 1. Let's say light is incident at theta 1 and it bends at a certain angle which is theta 2. Similarly, the same light beam can actually hit, you are essentially having plane waves which are incident on this. So you're going to have, I'm sorry, my drawing is not very neat, but this is my angle of incidence, and then there is an additional wave which bends like this. So one important feature to recognize is, what is the path difference between these two rays? So there is one ray which is incident on the first slit and the second ray which is incident on the second slit. So how much is the path difference? And that we can actually calculate using geometrical arguments. So I'll simply create one perpendicular direction line here like this, and there's another perpendicular line like this. So after all, this is a plane wave, so all the phase fronts are parallel to each other. Only the difference is going to come in this section, additional path difference. Okay, so now like that I'll do for both sides, and I'll highlight this as this stretch is the path difference. What do we mean by path difference? It's essentially the extra distance that the second wave is traveling because of geometrical arguments. Okay, so now this is a theta, so I can immediately say this is 90 minus theta, and this is going to be theta 1, and this is going to be theta 2. So if you have such a scenario, I can even label this for the first medium delta 1, second medium as delta 2. So my path difference is going to be equal to delta 1 plus delta 2. And what is the path, optical path? We have introduced the idea of optical path, which is simply the physical distance times the refractive index. So in this case, if I say this is my medium 1 n1 and this is a medium 2 n2, so I can talk of the path difference as n1, this is cos theta is in this direction, so sin theta 1, sin theta 1. Of course, there should be an a, I'm sorry, I missed that. n1 a sin theta 1 plus N2A sine theta 2. These are the path differences. So my total path difference is going to be N1, the combination. And something interesting happens when that total path difference is equal to m lambda. It's an integral multiple of lambda. What happens there? Well, I mean, then you have constructive interference, okay, of the two waves, two rays which are coming from both the slits. Or you can have destructive interference depending on the condition. This is a condition for constructive or destructive interference. And you will see that you can just rewrite this, and let me, just consider for a moment that, okay, let's do this. So I can write it as N1 sine theta 1 plus N2 sine theta 2 is going to equal to m lambda by A. Okay. And for a moment, let's consider a scenario where N1 equal to N2 equal to 1 and normal incidence theta 1 equal to 0. So what happens in that case? You simply have n sine theta 2 is equal to m lambda by A. What is this telling us? If you take a moment and observe, let's consider a situation where lambda is 500 nanometers, okay, and let's say A is 100 nanometers. My lambda by A is going to be 5, okay. In that case, this equation will not be valid for any particular theta 2. It doesn't matter because sine theta is always going to be in the range of 0 to 1 or minus 1 to 1, right? This guy sine theta 2 can be in range of minus 1 to 1. So you have to have, m in this case, m is an integer. Okay. So when you have a scenario where lambda is much greater than A, let's consider another scenario wherein your lambda is, let's say, 100 nanometers and A is 500 nanometers. Okay. If I take lambda equal to 500 nanometers, A is equal to 100 nanometers. If I take this scenario, then I can have multiple combinations of m. At various m's, I can have this equation to be satisfied between 0 and 1. So what happens is, if I think of this as a diffraction grating here, and let's say my my grating is of this form, there are just, I'm collapsing all of that into one single line. So essentially you have transmitting and not transmitting regions. Let me say my light is inserted in the normal direction here. So of course, for m equal to 0, light is going to go down directly. That is what we call as a 0th order. But if you have other, other angles which are supported, then you might have various angles which are allowed. M equal to plus 1, m equal to minus 1, m equal to minus 2, m equal to plus 2, and so on. So basically, even for m equal to 1, 2, and so on, you can have a situation where the equation is satisfied. So basically, that particular angle, let's say if you have a scenario where for some theta prime, I'll say, okay, the theta prime I can find in such a way that sine theta prime equal to 2 times lambda by A. Okay, for that it is satisfied. So in that case, the bending angle is going to be here theta 2 prime or theta prime. Sorry, I said this is theta prime, and this is also going to be theta prime. So you can have the second order diffraction that way. And if your m equal to 1, then you will have a first order diffraction. That's why we are numbering them as 1, 2, and so on. So what you see is, in the 0th order, all the wavelengths will go in the same direction as the angle of incidence. Okay, when m equal to 0, sine theta 1 equal to sine theta 2. In the case of n1 equal to n2, right? That has to be valid. But the moment you have different m's allowed, and for that you can have each wavelength will actually disperse at a different direction. So it is something similar to what you would have seen in a prism. So if you go back, and if you have in the basic school curriculum, they'll talk of a prism which has, let's say, the white light incident from the left, and then they'll say that, oh, there is blue which bends in one direction, red which bends in other direction, and so on. So you have the dispersion that happens, dispersion of light, right? This happens. Similarly, you don't need a prism at all. You can actually have simply a grating that has this sort of a variations, and you have light which is incident on that. If you have such a scenario, again, sorry, why is it? Yeah, you have light which is incident on this, it essentially disperses. Now, red, blue, green, and so on, red, blue, and so on, they'll disperse in various directions, and that's again dispersion of light. So a grating helps in dispersion of light. Okay. Another small tidbit that I just wanted to leave you with, because I'm going to use it in the next week, is how do you know which angle it is bending? Okay. For that, let me go back to the initial discussion where I said that, let's say if you have a medium, let's say n equal to 1.5, and you have medium from air which is on the top, and I consider a wave which is incident on this medium, let's say at angle θ1. At what angle that the wave exit? So we know from our basic school physics that it is n1 sine θ1 equal to n2 sine θ2. Okay. But it turns out that this can be looked at in a different way, and I already mentioned this. I said that you can think of it in terms of momentum conservation. So the k parallel, the wave vector in the parallel direction to the interface is conserved. K parallel is conserved. Why is it conserved? Well, in the parallel to the interface, there is no variation. There is spatial uniformity, right? So the symmetry is protected. There is no translation symmetry exists. So if you move from one point on the interface to another point on the interface, it's essentially the same thing. There's no difference in the environment. Because of that, we say that translation symmetry is obeyed along the parallel direction, and that's why the momentum, the k parallel is conserved. So when you have k parallel conserved, we immediately showed that in this case, if you have basically you have a wave which is incident in this direction, so you can think of a k parallel and a k perpendicular. Okay, so k parallel effectively is going to be, in this case, sine theta. Okay, so basically your k1 sine theta 1 equal to k2 sine theta 2. Okay, and that is why you will get the expression, this implies n1 sine theta 1 equal to n2 sine theta 2. Okay, this is what we have seen. This is background, So now what happens if you have a grating? Okay, what happens in a grating is, let's say in a grating, the momentum conservation should still hold, but now just like what you have, the boundary conditions, so the difference in the momentum should be equal to the grating vector. Okay, so in a grating what happens is, let's say k1 sine theta 1, let's say I'll take the difference in the momentum, so k minus k2 sine theta 2 should be equal to, I'll say m times g, where my g is a grating vector, which is simply 2 pi by periodicity. In this case, my periodicity was a, so 2 pi by a. Whenever you have such a scenario satisfied, you can have the diffraction or the refracted wave, right? So now let us consider with our easiest case, n1 equal to n2 equal to 1 and theta 1 equal to 0. So what happens? Now immediately you see that k2 sine theta 2, I'll simply drop the negative sign because I can always drop, that's okay. So or if mg by a, mg, the grating vector. So g is 2 pi by a and k is 2 pi by lambda. So you'll see that sine theta 2 is going to be minus some integer times lambda by a. Precisely is the same definition. I'm just, there is a negative sign that come in, but because of the way I defined it. But effectively for a grating equation, we saw that this is what you get when you have that scenario, wherein n1 equal to n2 and theta 1 equal to 90 degrees. So you see the same thing comes. So this sort of a analysis of thinking about the refraction as momentum conservation is useful, especially when you talk of, when you want to understand, let's say a scenario where light is incident from air into a photonic crystal. How does it bend? Okay, this sort of problems can be thought about using the ideas that I've discussed. All right. If not, let's stop here and I'll see you in the next lecture. Thank you.